Hello. So in this video, I want to talk about one of the most feared topics in all of mathematics, and that is calculus. Now in school, calculus arrives with a storm of new words: limits, derivatives, integrals. And we are made to memorize lots of rules and lots of formulas about these ideas. But rarely are we shown what these things really mean. In my previous video, I covered the idea of multiplying two numbers visually. What if I told you here that we had already started doing calculus? You wouldn't believe me, right? In this video, I'm going to show you how the visual idea of multiplication extends naturally to the heart of calculus, that is integration. We will see that while multiplication visually is about forming rectangles, integration is about forming infinitely many tiny rectangles that collapse across time. And we will see this without any formulas, with just a few clear and simple pictures. Now, to do a brief recap of what we saw in the last video. To multiply a number 2 by another number 3, what it means visually is simply repeat 2 3 times as such. So we have 2 and we repeat it 3 times. And we can notice the formation of a rectangle. So this rectangle is 2 times 3. And similarly, for any two arbitrary numbers a and b, to multiply them, we just repeat a, b times and form a rectangle as such. So this rectangle is a times b. That's all we need to know to go forward in this video. Now let's imagine that we have taken a long bicycle ride, where for the first hour, we ride at a speed of 5 kilometers per hour. For the next 3 hours, we're at 4 kilometers per hour. And for the last 2 hours, we're at 7 kilometers per hour. The question is, what is the total distance that we covered? Now, I assume from school we all remember that distance is speed times time. So this is really just a simple arithmetic problem where we take the time-speed pairs, we multiply them and add them up. And we get our answer, that is 31 kilometers. We covered 31 kilometers in total. Now, this is not a very interesting problem. What is interesting is, can we imagine what's happening here? Can we visualize what's happening here mathematically? So to visualize our journey so far, I have drawn a little diagram that records the information that we were given visually. So for the first hour, we traveled at a speed of 5 kilometers per hour. Now, the total distance that we covered during this time period can be calculated with the formula speed times time. And we know wherever we see a multiplication sign, we have to form a rectangle. So that's exactly what I've done. And now we also have a representation, a visual representation of the distance that was covered during this first hour. So the area within this rectangle here is the representation of the distance that we covered during the first hour. So that could be 5 kilometers, right? And I've done the same thing for the next half of the journey. For the next 3 hours, we travel at a speed of 4 kilometers per hour. So the area within this rectangle gives us the total distance that we covered during this time frame, which would be 12 kilometers. And the exact same thing here, this is 14 kilometers. So far, we have taken the information that we were given and recorded it visually. And I want to reiterate what we have done here. We were given information about how fast we went across certain intervals of time. We had the knowledge that distance is speed times time. And we had made the discovery that multiplication can be represented by drawing rectangles. So this allowed us to visually represent the distance that we covered across different intervals of time. We discovered that across the first hour, we covered this much distance. Across the next 3 hours, we were able to cover this much distance. And across the next 2 hours, we were able to cover this much distance. So the total distance that we covered visually can be represented by this entire conglomeration of rectangles. And to make this visually very clear, I'm going to rub out these barriers. I'm going to rub out these barriers. And I'm also going to do something interesting. So now I have removed the barriers between the different intervals of time so that we have a clearer picture of how much distance we covered across this journey. And I have also added some infrastructure to our picture so that we can conduct a deeper analysis of what is going on here. And what I've done is I've added an axis for time along this horizontal line because this is really where we were recording all of our time information. And I've added an axis for speed across this vertical line because this is where we were recording our speed information. Now, I want us to pay closer attention to what is happening over the first hour of our journey. Over the first hour of our journey, we have said that we maintain a pace of 5 kilometers per hour. But this is not entirely realistic because it could be the case that over the first hour of our journey, we maintain an average speed of 5 kilometers per hour. But what really happens is perhaps we start at a speed of 5 kilometers per hour, then we speed up a bit, right? Then we come down, and then we maintain that pace, and then we go up again. It all averages out to 5 kilometers per hour. But, when we ride a bicycle and, take on this sort of journey, we're always oscillating our speeds. And consequently, we can see that over this tiny interval of time, the amount of distance we cover is this. Over this interval of time, it's this. And then it stays there, and then it goes up again. We can see that as we become a bit more accurate with recording our speed information, the distance picture changes. Now I have extended this insight that we had across the first hour to our entire time frame, where all we are really doing is going from bigger boxes to smaller boxes. That is, instead of recording our average speed across a large interval of time, we are doing it across smaller intervals of time and seeing how that evolves our distance picture. So hopefully it is still clear to us that the total distance that we cover across this journey visually can be represented as a sum total of the area under these new green boxes. Hopefully that is still clear to us. Now we have certainly gotten far more accurate in representing what happens visually and mathematically across our bicycle journey. But if we want to get a real picture of what is going on, the true picture, we have to recognize that our speed in an actual bicycle journey is always changing. It can never be the same across any interval of time. That means if we take two successive tiny intervals of time, the speeds that will be exhibited during those two intervals will always be different. We will never be able to have a straight line like this. So, a more accurate way to represent the speed across our journey, across our bicycle journey, would be a curve of this sort that kind of traces out the edges of these boxes. Now, if the speed across our journey is depicted by a curve, what happens to our boxes? Our boxes become infinitely thin. They have no width anymore. This is a bit difficult to visualize. But if we imagine that at a time t, the speed exhibited by a bicycle is of this value. And at the very next interval of time, let's say t1, the speed exhibited by a bicycle is this value. We can barely see any type of box being formed. I mean, there is a box, but it has no width. It's infinitely thin. And in this way, if we can imagine that this curve, the speed curve for a bicycle, is made up of infinitely many thin boxes, then we can conclude that the area under this curve from time 0 to time 6 is the total distance that we traveled across our journey, across that time. And more specifically, the time, the area under the curve between any two intervals of time will represent the total distance that we covered across that interval. This is the key idea of integration.